Hey guys, I see a couple people on, so let me know if you got questions. Hi. Yep, sure thing, Nicole. All right. As always, let me know if this is not in focus or you can't make out what I'm doing, or I need to write bigger or something. Just let me know in the chat. Okay, so Nicole's asking about orbital diagrams, which are the more complex of the you can do the electron configuration or the abbreviated electron configuration, or you can do an electron orbital diagram, which gives you a little more insight into kind of where the electrons are at, how many orbitals are in each sublevel. So let's look at, say, something like, let's do carbon. Okay, so let's look at, if you can see that, the electron orbital diagram of carbon. So carbon is element 6, okay, atomic number 6. So that means 6 protons, which if we're talking an atom of carbon, it's going to have the same amount of protons and electrons because it doesn't have a charge. So it will also have 6 electrons. Okay, so we're going to do the electron orbital diagram for those 6 electrons. Okay, so starting out with the correct order, okay, we go to the first energy level, S sublevel, okay, which has 1 orbital. So we're going to actually draw out a line for that 1 orbital. Okay, and the first 2 electrons are going to go in there, and 1 is going to be spinning up and 1 is going to be spinning down. Really all we're getting at with that is that they're not in the same spot. They're not doing the same thing. Electrons are all negatively charged. They don't want to be next to each other. So if they have to both be in this same orbital, that same region of space, they're going to be doing different things. That's really all we go into it. So I'm going to draw an up arrow and a down arrow. Doesn't matter which one goes first, but just to show that they're not doing the same thing. Okay, so there's 2 electrons, 2 arrows. We got to get to 6. So after the 1s is full, now we're on to the second energy level, and again the s sublevel. Okay, spherical shaped orbital, which it's an s sublevel, so it only has 1 orbital. So we're going to draw again another line there, and then the next 2 electrons as well will go there. So up arrow, down arrow. So that gives us a total of 4 electrons. We're trying to get to 6, so we got to keep moving on. So next, after the 2s is still second energy level, but the p sublevel, okay, or the dumbbell-shaped orbitals, which for every energy level, there's 3 of those. Okay, there's 3 orbitals that are in in any p sublevel. Okay, so second energy level, p sublevel, 3 orbitals. We got to get to 6 electrons. We've used 2, 4, so we got 2 more. So we're going to put 1 of those in the first orbital, and then since all of these 3 orbitals are the same energy, that next electron is going to go with the same spin in the second orbital. Okay, so we're not going to pair them up unless we have to. Okay, so that would be the electron orbital diagram of carbon. The more electrons that we have, the more you just keep going. They get pretty long, and you just got to know the order. 1s, 2s, 2p, 3s, 3p, 4s, 3d. So make sure you know that order, and then make sure you fill in electrons unpaired, as we would say first. So with carbon, I'm going to put the 5th electron there and the 6th electron there. If we had another one, if we went one farther than carbon to nitrogen, which has 7 electrons, we put that one there. And then if we even went another farther to oxygen, which has 8, that 8th electron is going to start pairing up again. Here, there would be the 9th, there would be the 10th. And then once this whole thing is full, then we go to the next energy level, sub-level, whatever's next. Okay, so Nicole, let me know if you need another example of that or needs more clarification. Can I do a dimensional analysis problem? Elise, do you have any specific problem you want me to work on, like a metric conversion or a 2-step problem or units on top and bottom? Type in something if you have any more requirements on what problem you want. Okay, Lily says, can you go over? Okay. All right, so I'll just do a basic one. Okay, so a basic dimensional analysis problem. So let's say, I'm going to just go really basic. Let's say we have 3.75 feet. Okay, we're going to talk a unit of length. Okay, feet. Okay, and we want to turn that into inches. Okay, so we want so many inches. Okay, to do this, I have to change dimensions. I have to get this from units of feet to units of inches, which are both units of length or distance, or however you want to say it. So we can do that. It's not like going from units of mass to time, like that doesn't really work. But we can turn length units into different length units. So if we want to turn feet into inches, this should be a simple problem. We're going to do dimensional analysis, which means we're going to multiply by some conversion factor, which is a fraction. Okay, it's essentially equal to 1. Whatever we put up here and on the bottom, those are going to be the same distance. So essentially, we're multiplying whatever we started by 1. We're multiplying whatever we started with by 1. So it's not changing the distance, it's turning it into a different units with a different number associated with it. Okay, so in order to get feet to inches, we're going to need to know how many inches are in how many feet. And I put inches on top here because that's what I want. I want feet to cancel out because that's what I'm starting with. So if it's on top over here, because essentially this is over 1, what's on top and on bottom is going to cancel out, and I'll be just left with inches. Okay, so I got to know that relationship. All your unit relationships you need will be on your sheet. Okay, so if you look there, you'd see, 12 inches is 1 foot. Okay, and then when we do this in the calculator, before we get there though, feet will cancel out. Okay, and then I'm going to try, see if you guys can see this. Maybe. for this problem, maybe I can scroll up a little bit. Might not work. We're going to give it a try. Okay, for this problem, the math would be 3.75. Okay, and then times 12, which is the top of the fraction. Okay, and then you could do divided by 1. Dividing and multiplying by 1 doesn't change anything. You know, if you want to be consistent, just do it. Go for it. So we'd actually end up with this being 45 inches. So I see, Elise, you're saying top and bottom units. Okay. Let's do one of those. I'll try and relate that to the truck problem, and then Lily, I'll do your problem next. Okay. So another dimensional analysis problem, kind of like the truck problem, even though I'm pretty sure it's not on your file. Let's say, okay, some company is producing, I don't know, 5,000 trucks, which we'll say is TR. Okay, so 5,000 trucks. They're doing that every, I don't know, day. Okay, 5,000 trucks a day. Okay, let's figure out about how many trucks that is. And I'm going to throw another thing in there. Let's say, let me think. I'm going to kind of go off on a limb, but I'm going to say, how many wheels is that per hour? So trucks to wheels is kind of a weird conversion, but we know every truck has 4 wheels. So let's turn that into how many wheels per, what did I say, hour? So we're going to do, make sure this is right, wheels over so many hours, HR. Okay. So top and bottom units, we got trucks over days, and we want wheels over hours. Okay, so how do we do this? Top and bottom units, we got to turn them both into something else. You only focus on one unit at a time. Okay, we can only cancel out one unit, either the top unit or the bottom unit at a time, you know, essentially. So let's focus on, let's do days. Let's do days. Okay, that is generally the harder one because it's on the bottom. So if I want to get rid of days and I want to turn that into hours, I'm going to have to multiply by a conversion factor. Okay. Now the one thing people normally mess up here is days starting on the bottom means that days has to go on top of your conversion factor. Okay, and then do we know how many hours are in a day? Yes. Okay, we know 24 hours are in one day. So we can use 1 day over 24 hours to convert from days to hours. Days starts on the bottom, because it's trucks per day. It's on the top of the conversion factor, so it'll cancel out. Okay, so that will get rid of days, and I'll kind of just like scratch that out so that you see, all right, days is gone. So if I did the math, if I just stopped here, I would have 5,000 trucks per hour, per 24 hours. Okay, but we want wheels per hour. So this is kind of a weird, I may be stretching this a little bit, but we know that 4 wheels come on every car. Okay, maybe it's got a spare, we won't worry about that. So just 4 wheels we need to make a truck. So I can convert trucks into wheels. Okay, trucks starting on top. So we're going to put it on the bottom of this, and then I'll just do like W per wheel. Okay, so how many wheels equal how many trucks? Well, 1 truck is going to have 4 wheels. So if I wanted to figure out how many wheels they're making per hour, I would do this math. Trucks here would cancel out with trucks in the beginning. Okay, so we'd have 5,000 times 1 if you wanted, divided by 24, times 4, divided by 1 if you wanted to do that. Doesn't change it. Okay, so if I did that math, we'd get that. This company must be making 833, not worrying about sig figs, so just to say that it's 0.333 wheels per 1 hour. That's what we'd end up with. So Elise, that was using top and bottom units to cancel them out. And it only took 1 step to do each. So only 2 conversion vectors, 1 to convert the top, 1 to convert the bottom units. Sometimes they're more, but also it's the final, so it's kind of just a general knowledge of everything. It's not, you're not going to have like a 7-step problem on your final or anything like that. Cool. Okay, let's go to, so Lily. By the way, are you guys all together? Because you emailed me like the same thing 4 times. Question 45 on the review guide. Okay, I'm going to have to look that up. What is the quantum of energy released from 440 nanometers of blue light? All right, so that is a tough problem, more tough, or one of the tougher problems if we're talking about light equations. I pull it up yet? Nope. All right, so while that's kind of pulling up, this should be number 45, okay, on the review guide. And it says, how many, or no, this is the right one? No, I must have changed something because now it's 44, at least on my copy. Oh, well, so what is the quantum of energy released from 440 nanometers of blue light? So if we have a photon of light that is 440 nanometers, okay, that's the wavelength, 440 nanometers. Might be around the blue light, doesn't really matter. You don't need to know those for your final, but kind of as review from last night, you do want to know the spectrum though, and which ones come first and have higher wavelengths or shorter frequencies. So make sure you guys know that. So number 45, okay, we have 440 nanometers as our wavelength. So let's write that down. Okay, that's the kind of weird looking squiggly thing. And we want to turn that into energy. Okay, don't get confused by quantum of energy. It's just what's the energy. Okay, it's just some amount, some quantity of energy that's associated with light that has that particular wavelength. So if you guys look on your units and conversion factors sheet, we go to the back. In the top left corner, there's a bunch of stuff on here. We haven't gotten to a lot of it yet this semester. We won't really get to much of this till the next semester, where we'll start using a lot of different equations. So in your equations, we got the density one. You'll definitely need that. And then the 2 equations below it, those are the light equations. We're going to need both of those here. Okay, and then over on the top left, under the constants, there's speed of light, which is c, and Planck's constant, which is h. We're going to need both of those as well. Okay. So let's write those equations down. Speed of light equals wavelength times frequency is v. And then energy equals Planck's constant also times v. It's actually like Greek letter nu, lowercase, don't really need to know that. But v is frequency. Sometimes you see it as f. We're going to use v. Frequency relates both of these equations to each other. Okay? In each equation, there's also a constant. It's either the speed of light. We know that in this equation. Hopefully, you programmed it into your calculator if you have one of the fancy ones. And then Planck's constant is also another constant that you just know. So those aren't going to change. So in each equation, there's two variables that could change. Okay, or sorry, these two. Okay, so we got wavelength. So we got this equation. We got the wavelength there. We want energy, which is over here. So we're going to have to use both equations to get what we want, which is energy. Okay, if we were given like frequency, you know, I could just multiply by Planck's constant to get energy, but I was given wavelength, which is over here. So first, we got to use wavelength and the speed of light to calculate frequency. So we got to rearrange this equation where we're going to have that frequency is actually the speed of light over wavelength. Hopefully you guys can see that. Okay. So if we're going to solve that, it's going to be again, and actually before we get to that point, real quick, speed of light is 3.0 times 10 to the 8th meters per second. So that's C, that's that number, and we're going to say meters per second. If I put 440 nanometers on bottom here, they're not going to cancel out because I have meters on top and I have nanometers on the bottom. So I have to convert nanometers into meters. So if we go back to our metric system, look at that underneath would be, okay, so meters is what we want. That's the base unit. There's no prefix. It's just meters. And we're going to compare that to nanometers, okay, which is nm. There's a couple ways you can do that. There's the meaning you can use. There's the power of 10 you can use, which I recommend. A lot of people, I would assume, probably use the relation to meter because it relates that unit back to the base units. You can use those. Essentially, if you guys want me to go through this conversion, let me know in the chat. I'll kind of try to see pay attention to see if you guys say that. But essentially, nano is times 10 to the negative 9th, and base unit is times 10 to the 0. So what I teach is you take the difference of those powers, which would be 9. So the relationship is either going to be 10 to the 9 or 10 to the negative 9, depending on how you look at it, which I can definitely review. Or because we're going to the base unit, you could just look here and you will get one of those relationships. Here it's saying 1 meter is equal to 10 to the 9 nanometers. Okay, so we could use that relationship. You could do the dimensional analysis there to convert from one to the other. I'm just going to say, if you're ever given nanometers, which is common because that's what visible light is the units for visible light is, they're in the area of nanometers, so that's how we kind of talk about them a lot. Just take whatever number you have in nanometers and multiply it by 10 to the negative 9th. Okay, so this would actually be 440 times 10 to the negative 9th. Okay, and that's going to be just meters. So again, if you guys want help explaining why we did that, I can do that again in a separate problem to show that. Okay, so we got to get this to meters. We got nanometers to start. We need it in meters because the speed of light is in meters per second, and we need these to cancel out so we can be left with just per second with it, which is hertz. Okay, so if I do the math here, punch in the calculator. Okay, speed of light programmed in, 3.0 times 10 to the 8th, and then I'm going to divide that by 440 times 10 to the negative 9th, and you might want to put that in parentheses or potentially use the EE button because it could get screwed up if you don't. Okay, so speed of light divided by 440 times 10 to the negative ninth. That gives us a value of about 6.8181, and it repeats. But remember, also, we need that times 10 to the 14th. Okay, and that is hertz, which is per second. Okay, 1 over seconds. Meters, they cancel out. And because that's per second on top, it's actually like seconds are on the bottom. So we're just going to call it hertz. Keep in mind that is frequency, which has the units of hertz. Okay. So that gives us frequency, which now we can bring over here. I'm not going to move that over. So I got some more room. Let's rewrite this equation. E equals h times v. So energy is what we're looking for. H is a constant, and we just calculated for frequency. So we can plug in H, which is, we'll write it out. Looking at the handy-dandy sheet, 6.63 times 10 to the negative 34th. And the units for that are joules seconds. Okay. And we're going to multiply that. So that was all H. It's all H. We're going to multiply that times the frequency, which we just calculated from that previous problem over here, which was, it was 6.81 repeating times 10 to the 14th. And that was hertz, which here I could write as 1 over seconds. And that might show you a little better how seconds are going to cancel out here, because this is 1 over seconds, and that's just seconds. So seconds actually cancels out when we multiply these together. So we do Planck's constant, 6.63 times 10 to the negative 34th times 6.81, 8181, a couple more of those. Okay, times 10 to the 14th. Okay. So if I punched everything in my calculator correctly, we should end up with 4.52, and then some more digits. And if you guys can see this, I want to just show you something, because another common mistake people do, hopefully you guys can see that, is we get this big long number, okay, 4.5, and eventually I'm like, just cut it off after a couple digits. But you gotta keep the times 10 to whatever in that number, okay? There's a big difference between 4 and 4 trillion, So all these kind of digits in the middle here, sometimes we don't necessarily really care about those. You need the beginning ones, and you need that times 10 to the whatever there. Okay, so our answer is 4.52 cut off there times 10 to the negative 19th, and that's going to be joules, because seconds there is going to cancel out with seconds there. So, Lily, let me know if that works. If you guys want me to explain again how I went from nanometers to meters, I can do that with more work as opposed to just saying, like, accept it. So yeah, let me guys know. Let me know. Okay, yep, let's do it. So that one step where we have 440 nanometers, okay, and we want to turn that into meters, okay? How do we do that? This is just going to be a dimensional analysis problem, okay? Probably only one step. There's multiple ways to do this, but I would probably do only one step here. How I teach is, and there's like one of the only videos I've actually made on this YouTube channel is explaining this essentially. So you might go check that out if you want to kind of review this. So if I want to go from nanometers to meters, to cancel out units, I'm going to need nanometers on the bottom and meters on top. Okay. And I got to figure out that relationship of meters to nanometers. So we go back to the metric prefixes because that's all it is. It's just metric prefixes, these numbers that we can put in front, or these terms that we can, prefixes that we can put in front of units to make them mean bigger or smaller units by some factor of 10, by some power of 10. So it's really nice. Whereas, like 1 foot is 12 inches. 12 isn't a really nice number, but 10 is. So like how 10 decimeters is 1 meter. That's really easy. Okay, so here we're talking about nanometers, which is nm, and then no prefix, just meter. So how do you go from one to the next? How I try to teach you guys doesn't work for everybody because you have to have a little bit of a math brain to do this. Is I use these powers of 10. Okay, and we're always comparing 2 units. So here we're comparing the base unit, which has a power of 10 to the 0. So pretty much nothing. It's like times 1, so it doesn't change. And then nano is 10 to the negative 9th. So what this 10 to the negative 9th is saying is that 1 nanometer is 10 to the negative 9th meters. Just like this 10 to the negative 12 for pico. That's saying 1 picometer is 10 to the negative 12th meters. Okay, so these are all really small units down here. Okay? Up top, those are big units. A megameter is 10 to the 6th meters. Okay, so we're looking at a small unit, a nanometer, a small unit. So 10 to the negative 9th here, 10 to the 0 there. Now there's 2 relationships we can get. We can say I have one of one of them, how much of that is the other, and then I can kind of flip-flop. So I'm going to get 1 of one of the units, and then either 10 to the negative 9th of the other or 10 to the positive 9th, depending on what you're looking at. Is it a big unit or a small unit? You're always going to have a smaller number of bigger units equals a bigger number of smaller units. Okay, so you could use those. So if I was going to use those, I would come here, back to dimensional analysis, and it doesn't matter which one we put 1 here. Okay, let's say to make it the same as the power, let's say I got 1 nanometer. Okay, so 1 itty bitty nanometer. That's going to be 10 to the negative 9th meters. Okay, so that power that was on the sheet, I put that there, and I just put 1 nanometer. Okay, because that's what that power stands for. So one really small thing is a super small fraction of 1 of that bigger unit. Okay, meter, which is about as big as a yard. Okay, so I can use that relationship. If you did it the other way, if you wanted to multiply by 1 meter over so many nanometers, that would be 10 to the positive 9. Okay, because 1 meter, which is about as long as if I kind of spread out my arms, maybe a little less than that. That's going to be 10 to the 9th, a huge number. That's like a trillion, billion, a billion nanometers. Okay. So you can use either of these relationships. You'll get the same number. Okay. So let's just go back up to this one. So 440 nanometers, we're going to multiply that by 10 to the negative 9th meters over 1 nanometer. Okay. And when we punch that in our calculator, I'm going to kind of write a couple things it could say. It could say, just without actually even punching it in the calculator, we're dividing by 1 here. So essentially that's not really doing anything. So it's really just 440 times 10 to the negative 9th. Okay, so 440 times 10 to the negative 9th. You could end up with that. Your calculator is probably going to put it in scientific notation. So your calculator is actually probably going to move the decimal and it's going to say, oh, that's 4.4 times 10, or E, to the -7th. I moved the decimal 2 spots, and that took away 2 powers. Look at it, your calculator is probably going to say 4.4 times 10 to the -7th, or it would say 440,000,000,000,000 with like 9 zeros, 10 including that one. So there's a couple different things. If you want help, I can train you, or I can teach you how to make your calculator tell you the scientific notation or not tell you, because you can change that setting. So that's essentially how we end up with the meters for that problem. Real quick, if you're just like, I don't understand, on the last column there's the relationship to meter. You can also use that, and that actually just gives you one of the relationships we talked about. It says 10 to the 9th nanometers equals 1 meter. Why I don't like this as much is because it relates everything back to the meter, which is good, and in this instance it also works for this problem. But what if I want to compare a kilometer to a micrometer? It doesn't give me that relationship. So there, I recommend using the powers, because you could just take the difference of the powers. But you could do like a 2-step problem with those as well. Okay. Hope that helps. Let me know if you are still confused, you want me to do another problem or another conversion or something like that. And remember, if you're on here, which I think it's mostly the people that have just commented, but if you ask a question throughout today, yesterday, or tomorrow, I decided I'll give you 2 bonus points. So if you got, for those of you that asked the question last night, I gave you those bonus points, and it should say like +2 for asking a question or something like that. So if you haven't asked one yet this week, you might do that. I'm going to record the people that I didn't get yesterday. Tuli said, no, just for one day. I just kind of wanted to get people to like get here, so that if they actually had lots of questions, you can ask as many questions as you want. I'll try to get to them. But I was just doing the bonus points for just one question. All right, so Lily, there's a question on the study guide, it's number 43 on mine. But the question is, what is the electron configuration of the element in group 4 and period 5 of the periodic table? Okay, so that's a good question. Someone asked about that today. So let's get a new sheet. I'm gonna rip my periodic table off the wall so we can look at that. All right, so periodic table. So group 4 and period 5. Okay, group 4, they're labeled. So I'll go over here, and it actually means group 4A. So I should probably change that, because I use these numbers in this system. So that really means 4A, not this group 4 here. I'm going to change that because I don't like how that is worded. Okay, so really it's talking about 4A, okay, which is also group 14. Okay, so that is the group. Okay, it's that column. Okay, so carbon, silicon, germanium, tin, lead, flavorium, that column. And then it says period 5. Okay, so don't make the mistake of starting from carbon, because carbon's actually the second period. First period only has 2 elements. It has hydrogen and helium. So first period, second period, third, fourth, fifth, okay, that's going to be 10, which is in, again, the group 4, which I'm going to say is 4A, and 14, or also 14, and then period 5. Okay? So 10. So we want 10's electron configuration, and this is number 43, or maybe like 44. depending on when you got your practice test for the final. Okay, just gonna orient myself there. Okay, so we're looking at tin, if I remember correctly. So tin is element 50. Okay, so its atomic number is 50. So that means if it's an atom, okay, not an ion, if it's an atom, which means equal number of protons and electrons, then we have 50 electrons that we have to account for. Okay, so electron configurations, you need to know that order of energy of the orbitals and the energy levels and the sublevels, what order we go in. Okay, so we're going to start with the 1s, and then I'm going to keep going with that just so you guys know the order, and then we'll add in the exponents. So first is the 1s, then the 2s, okay, then 2p, then 3s, then 3p, then 4s, okay. After the 4s is actually the 3d, okay, if you remember that. And then past 3d is back up to the 4 with the p sublevel. And then after that, back down to energy level 5s. Okay, after energy level 5s is going to be the 4d. And then after the 4d, back up to the 5 again with the p sublevel. And that's where I'm going to stop, because looking at my periodic table, I can see that tin is in the p block, and it is the fifth row, fifth period, fifth energy level. Okay, so I'm going to end with 5p, and then we'll probably do the ending right now, because that's really what matters. We'll go back and fill all these in, make sure they're full. But this is going to end 5p2 because it's the second element into the p block. If you guys remember that, let's look at the periodic table. Okay, so tin is in, go down a little bit. And tin is in the 1, 2, 3, 4, fifth period. Okay, fifth energy level. Okay, it's in the p block, which is this block here, and it's the 1, 2, the second element in. Okay, so it should end. Let me get this all in there. Should end 5p2. Okay, so if that's where it ends, and that fifth energy level p sublevel is not full, everything else before it will be though. Okay, everything else is always full, except for if you have a question like, what's an example of an excited state? That would be an example of like an electron from one of these lower energy levels, being up here. So having a not full energy level, that's not your last one. Okay, so if we go back, let's maybe go in order from the beginning. Okay, starting at the 1s, that's an s sublevel, so it's going to be full with its 2 electrons. 2s, also an s, so it's going to have its 2. Then onto the 2p. P has 3 orbitals, 2 electrons each, so 6. 3s, s only has 1, so 2. 3p is going to have 6, or s2. 3d, so d's have 5 orbitals, so that's going to be 5d10. 4p6. 5s2, 4d10, and then we're back to 5p2, and we end there. Okay. Yeah, so Sebastian, if you rewind, I should be going over that one. A little bit before this is me doing the conversion of 440 nanometers to meters, which you have to do in that problem. Before that, I do that problem probably like 20 minutes ago. All right, Rebecca, can you go over number 73 on the study guide? which asks how to find the total number of atoms represented by a formula. Okay, so let me go look at that. I changed some stuff at one point, so I want to say it's 70. It's my 74, I think. Okay, so it might be your 73. 73, 74, somewhere around there. Problem asks the formula for ytterbium, or terbium, however you're going to say that, sulfate, okay, is YB. Nope, wrong question. What is the formula? Nope, yeah, it is 73. That actually is 73 on mine. The number of atoms of oxygen indicated by the formula Ca3PO42. Okay. Let me write some stuff down here. Sorry if this isn't in focus. I can't see what I'm doing right now. So I just got Ca3PO42. Okay. Atoms of oxygen, question mark. Okay. So let me go back to see what I'm doing. All right. Make this a little better. Okay. So calcium phosphate. This is calcium phosphate, formula Ca3PO4, in parentheses, because it's a polyatomic ion and we need multiple of them. We need 2 of them. Okay. How many atoms of oxygen are here? So for calcium phosphate, this is the only formula we get. It's an ionic compound. It's made of charges. Calcium has a positive 2 charge. Phosphate has a negative 3 charge. So that's how we get that formula. So if I want to count up the atoms of oxygen, or any of the elements, I look at my formula. Okay. If anything's in parentheses, whatever is outside applies to everything in the parentheses. So this 2 here applies to that O, which has a 4 as a subscript. It also applies to that phosphorus, which has an imaginary 1 as a subscript. Okay, so if I want to know if I have 1 calcium phosphate, I just have 1 formula unit. Okay, I'm going to have in total 3 calcium atoms. Okay, so 3 Ca, and then 2 phosphorus. And then for oxygen, which we're actually kind of, what the question's asking about, we're going to have 2 times 4 oxygens. We have 8 oxygens. Okay. If I just had 1 formula unit, one of the most basic unit of calcium phosphate, at the very least, I have 3 calciums, 2 phosphoruses, and 8 oxygens. Let me know if you want more clarification on that. I hope that helps. And that was number, I think number 73. Eli, I don't know what that means. Let me know if you guys got any questions. We're down to only 2 people, so maybe not. can I go over simple atomic structure, wavelength, quantum energy? And touch up on trends. Yes, so atomic structure, I will write out the symbol so that you know what that all means. Wavelength and quantum of energy, I did a problem earlier, maybe like 10, 20, 30 minutes in, where we have a wavelength of 440 nanometers, and we want to turn that into energy. Two-step problem. It's number 45, 44, 46, somewhere around there on the study guide, the practice test for the final. So Eli, check that out. In terms of atomic structure, you really want to know, definitely go over the notes for atomic structure and history on Unit 2. You'll see a symbol that looks kind of like this, and it has an A down there and a B over there and a C there. If you, number 45. I did that earlier, so make sure you check that out. So you see this symbol in the notes. I use ABC. Some sources do differently. I like ABC because A fits well with atomic number, which is the number of protons, which tells you the element. Okay, well, however many protons you have, that is the element. B is the mass number, which is equal to the sum of the two particles that make up 99.99% of the mass. Both of them contained in the nucleus. That's the protons and the neutrons. Okay. So mass number is protons and neutrons together. Okay. And then C, I also like using C there because that is the charge. You don't always have a charge. If it's an atom, there is no charge because protons and electrons are the same amount. Charge is determined by protons minus electrons. And I do it that way. You also sometimes see that differently. It's just the number of protons minus the number of electrons. Yes, electrons are negatively charged, but I do not put a negative, however many there are, because a negative minus a negative, or subtracting a negative is going to actually add, so you get like a huge charge. Okay, so if you want the charge, it's protons minus electrons. I like it this way because if you have more protons, it's going to be a positive number. If you have more electrons, it's going to be a negative number. Okay, and that makes sense because the more positive things you have, the more positive it is, the more negative things, the more negative. Okay, so you want to know that symbol. You want to be able to calculate if I give you anything. If I give you the neutrons and the mass number, you can subtract mass number minus neutrons to get protons. That will tell you what element it is. You can figure out the charge if I give you protons and electrons. If I give you the charge and I give you electrons, you can figure out the protons, or any combination of those. You should be able to figure out, the thing you're missing. Okay, so make sure you know that symbol. Make sure you can do atomic structure practice. On the website, there should be one with an answer key that has a bunch of problems. It's just going to be a chart with some things filled in. You got to fill in everything you don't have. Okay. In terms of trends, there's 3 you got to know. Okay. And they either go up and to the right, they increase, or down and to the left, they increase. Okay. 2 increase up and to the right. Ionization energy. Okay, increases up and to the right, and so does electronegativity. Okay, both of those increase up and to the right. Hey, Wesley. Though they do have different elements that have the highest value for them, and that is because for electronegativity, we ignore the noble gases. So all the way up and to the right, if we're looking at the periodic table, okay, helium's all the way up and to the right. It has the highest ionization energy. Okay, it is really hard to take an electron from helium. Okay, it's the hardest. It's super stable. It doesn't want to do anything. Okay, electronegativity is the pull of electrons. How much a certain element pulls electrons, hogs the electrons in a bond. Okay, so if something wants electrons more, it's going to have a higher electronegativity. Helium doesn't want electrons. Okay, it doesn't bond. So we can't measure its electronegativity. So we just like negate the noble gases, and we look at fluorine as the highest electronegativity, and we don't worry about helium or neon. Okay, so fluorine has the highest electronegativity. Okay, and then increasing down and to the left, that's atomic size. How big an atom is, how far the electrons are from the nucleus. So down and to the right, atomic size increases. And if you're looking at your periodic table, we can get that back out again. Francium would be most down and to the left. When I'm saying down to the right, I mean down to the left, whatever I'm saying, okay? Down to the left, atomic size gets bigger. So I'll write like francium there to show you that that would be the biggest. Okay. So ionization energy, electronegativity increase up and to the right. Helium has the highest ionization energy. It's the hardest to take an electron from. Fluorine has the highest electronegativity. It hogs electrons the most. If you look on the back of your periodic table, it has 4.0 for the value of electronegativity. No other element is as high as that. And atomic size increases down to the left. Francium is the biggest. Alkali metals, which are all farthest to the left, those are the most reactive because they're so big. The electrons are very far from the nucleus. They're very easy to just take for some other element to just take and have a chemical reaction. So Eli, I hope that helps. No, let me look real quick. Sorry, I just blew the paper everywhere. No, Eli, there shouldn't be anything on thickness on calculating that. All right, guys. Well, it is 4:30. If you have any other questions, I'll be on tomorrow. I'll be at school at 7 a.m. tomorrow. After school, potentially. Remember, it's a half day, though. So you can also email me. So if you guys have any questions, let me know. I will see you guys later.